Hello everybody, welcome to the first After Hours session. Before we begin, I want to basically explain what's the point of these sessions. So the first point is just to summarize what we did in the lecture. The second is to give more intuition into what we did, to relate our work in class, give it some geometric interpretations, physical interpretations, to somehow relate it to real world problems, and to make sure you understand everything better. So let's begin. Almost every lecture will be accompanied by an interactive component. The point of the interactive component is to help you understand better everything we do in this session, or sometimes things we do in the lectures. So for today, I want to speak about stability of systems. So this is a prerequisite knowledge, but just to make sure we're all on the same page, by our standards, by our definitions, we say that the system is stable if all the eigenvalues of the homogeneous matrix, so like the A for state space systems, or all the poles of transfer functions have negative real value. Okay, so what does it mean? So here we have this nice interactive plot. Here we take a 2x2 system and we plot its poles. So here on the right you have the poles, and on the left we have the step response. So when the system is stable, we expect the response to go to some finite value as t goes to infinity. So here you see I have a slider for the real part. The more negative the real part, the more left the poles will be. And as you can see, as long as the real part is negative, the response goes to some specific finite value. The second I let the real part be real, you can see that the response increases and increases, and it will actually go to infinity. This is why we always want to make sure all the poles, all the eigenvalues have a real negative real part. Now, if I let the real part be 0 exactly, then the response, as you can see here, the real part is 0. Then the response will be purely oscillatory. Now, the frequency of the oscillations is given by the imaginary part. So the larger the imaginary part, the further away it is from the real part. Oh, very small, it's very close to the real part. And basically, the omega, the imaginary part, is the frequency itself. So as long as we will have this imaginary part, the response will be a little bit oscillatory. So let's say we take the real part to be minus 3.1. You can see we go to some specific finite value, but the response is oscillatory. And if we make the imaginary part larger and larger, then the response will be more and more oscillatory. If the imaginary part is 0, then we will just go straight to our stabilizing value. Now, specifically, if the real part is more negative, this response will decay faster. So let's say we let the real part be -1, and then again we let the real part be -5. You can see it goes to our finite value much faster. If we take larger values of time, we can actually see that. And if we increase the real part, it takes a while longer to get there. Okay, so that's the point of stability. Now moving on to the lecture, I want to introduce notebook LM. I guess most of you or some of you know about it. The point of this notebook is that when we work with a large language model like ChatGPT or Gemini, When we ask him a question, he goes out to the internet to search for answers, and sometimes it causes problems because he just answers no matter what, and sometimes he says things which are not really true or false, and so on. Here in the notebook, the entire knowledge of the model comes from what we put into it. So like here, I took the lecture 1, I put it inside this notebook, and that's his entire knowledge. So when I ask him stuff, he actually goes to the lecture notes and he responds with respect to them. Now, this really minimalizes the mistakes the model makes. It still makes some mistakes, but it's much nicer. And it's also good at making infographics and cool graphs. So let's go over what we learned today. Basically, there are two main things we did in the first lecture. The first one is we spoke about linearizations. Under linearizations, we had two methods. We actually spoke about using the Taylor approximation to approximate our systems into linearized systems. And we also spoke about Jacobian matrix in this regard. In a few minutes, we will go deeper into that. So that's the first thing we learned today. And the second thing is we spoke about solution of linear systems. Here we had two cases. First, we had the LTI systems, and the solutions of LTI systems is the matrix exponent. We will speak about it in a moment. And we also had LTV systems, and their solutions is some state transition matrix. Okay, so to get more specific, let's go into some nice infographics. So first of all, let's speak about linearization. What's the point of linearization first of all? The point here is that every time we are planning a control system, we have a nominal plan. The nominal plan is the trajectory we would like the system to behave like. So let's say we are planning the movement of a drone in space. We want it to go over some curve, some trajectory, and that's the nominal plan. Now, the real world is not perfect, so maybe our mathematical model is not perfect, or maybe we have some perturbations and disturbances in the systems and so on, and the actual behavior of the system in real life will not be the actual nominal plan. Now, the point of linearization is that we assume that the actual state is equal to the nominal state, the nominal plan, plus some relatively small error. And we do the same assumptions for the controller. So the nominal controller, the controller which brings the system to behave like the nominal plan, that's U0, and U itself is actually the controller which brings the system to behave like the actual state. So we assume delta x and delta u are first order small approximations. This means that if, let's say, we have delta x squared, we assume it's 0 or any larger power of delta x. If we have delta x times delta u, we assume it's also 0 because it's not a first order term. In the sense that we assume that delta x is small, so then cosine of delta x is approximated by 1, sine of delta x is approximated by delta x itself, and so on. What we do in the first method is that we actually take this x, we plug it into our system, into the differential equations. We do all these approximations, and when we finish doing all these approximations, we end up with a linear system. So the linear system will be for the small error, not for the nominal state or for the actual system. So this is what we end up with, and of course we will also have an output. So that's the first method. I call it like a brute force method. The second method is quite nicer because it gives me a closed form expression for A, B, C, and D. And this method uses Jacobian matrices. So basically, we need A, B, C, and D, and here we have the formulas. So I just want to remind you, a general system is x dot equal to f, and the output, general output, is y equal to g. So f and g are some vectors, just columns. And state A is the Jacobian of f with respect to x, the input is the Jacobian of f with respect to u, and so on. So what does it mean? Here we have an example with A. So to compute A, we take the first element, the first entry of the vector f, and we differentiate it with respect to x1, this will be the first element of A, then with respect to x2, this is the second, and so on. So every row of A is taking the ith row of A is taking the ith entry of f, and then differentiate it with respect to x1 up to xn. This will give all the entries of the ith row. As I said earlier, this notebook LM is very, very nice, but still it makes some mistakes. So here the last row is actually fn. So we take the last entry of f and we differentiate it with respect to x1 up to xn. And I think if this is clear, then all other matrices are clear. So for B, we do the same, but we differentiate with respect to the entries of U. And the output is also very, very similar. So this is linearization. Now, moving on to our systems. We spoke about LTI systems and LTV systems. Let's see what's the difference. So first of all, LTI systems, LTI stands for Linear Time-Invariant. So time invariance means they are invariant in time. They are not affected by time, but in the sense that A, B, C, and D do not change with time. So we have x dot equal to ax plus bu, y will be cx plus du, A, B, C, and D are just constant matrices. In this case, the solution will be, as we said earlier, matrix exponentials, and specifically the solution, the general solution, is given here. So we will have the homogeneous part, which will depend on the choice of initial condition, and we have a non-homogeneous part, which will depend on our input. So that's LTI systems. Next, we have linear time-variant LTV systems. So time variance, the system varies with time, again in the sense that A, B, C, and D vary with time. So we will have x dot equal to ax plus bu, and A and B will depend on time. C and D might also depend on time. By the way, by definition, it's enough that only one of them will depend on time for the system to be LTV. For the specific state transition matrix, we need A to depend on time. But in any case, this general solution will depend on this state transition matrix, and the actual solution will be very, very similar to the LTI case. So instead of the exponent matrix, we have this phi matrix. Now, how do we actually go about and compute said matrices? So we have the final infographic for today. So for the exponential matrix, we have two methods. We can just compute the inverse of Si minus A and then take the inverse Laplace transform, in the sense that we just go entry by entry in the matrix and just take the inverse Laplace transform. So that's the first thing that we do. And for the second method, we can diagonalize A, and all the matrices we will see here will be diagonalizable, so it's okay. And actually, how do we do the diagonalization process? We compute the eigenvalues of A. From them, we can create this lambda matrix. It's a diagonal matrix with the eigenvalues of A along the diagonal. We compute the eigenvectors of A, and then each eigenvector becomes a column in this matrix T. And finally, the exponent matrix itself is just T e to the lambda T, which is just a diagonal matrix. Each entry is e to the lambda I T, yes, times the inverse of T. So it's quite simple. And it's a matter of taste how to approach this. Now, for the LTV case, first of all, by definition, the transition matrix is a matrix such that the solution at times t is said matrix times the solution at time t0. So I like to think of it as follows. t0, so here I have t0, and then I jump to t, which is here. Okay, so you can go and dismantle the equations and solve them one by one. You get the solution for each variable, and then you rewrite it in matrix form, and this matrix will just be the transition matrix. The second method involves the Wronskian. So what's the Wronskian? Basically, if we have a system of n first order differential equations, we will have n independent solutions. So I remind you that each solution depends on initial condition. If we take n different initial conditions which are all linearly independent, that's important, then for each such initial condition we can write the specific solution, and each such solution we put as a column in a matrix, and this matrix will be W, the Wronskian. Then the transition matrix is the Wronskian at time t times the inverse of the Wronskian at time t0. So this is how you do it, either in the first way or this way, and that's all quite technical. So this week's session was quite technical, but as we will go along with the course and the lectures, things will get more interesting in my opinion, more physical, more geometric, more related to real world stuff, and that's it. Thank you.